In this section, we're going to look at extreme values of functions. Let f be a function with domain D. Then f has an absolute maximum value on D at a point C if f of x is less than or equal to f of C for all x in D. So if the y value, all y values are less than or equal to this y value for all x's, then that value is the absolute maximum. Has an absolute minimum value on D at C if f of x is greater than or equal to f of C for all x in D. So if all the y values are greater than this y value in the domain, for all x's in the domain, then this would be our absolute minimum. Now, absolute maxima and minima are called absolute extrema, and they often depend on the domain. Here we are looking at the sine x function and the cosine x function only between negative pi over 2 and positive pi over 2. Now if we look at this sine y equals sine x graph, it has an absolute minimum of -1 at negative pi over 2. So we would say that its absolute minimum is -1. It has an absolute maximum of 1 at positive pi over 2. So it has a minimum of -1 and a maximum of +1. Now let's look at the y equals cosine x graph. The lowest points on this graph are y equals 0 at x equals negative pi over 2 and at x equals positive pi over 2. So the smallest y value on this graph of y equals cosine x between negative pi over 2 and pi over 2 is 0. The largest y value is 1, so it has an absolute maximum at 1. Now if we were to extend this graph of cosine x out, remember the shape of the graph, it dips back down to -1. So if we looked at just the cosine graph with no restriction on the domain, it would have a maximum of -1 and a minimum, or a maximum of 1 and a minimum of -1. However, since we're only looking between negative pi over 2 and positive pi over 2, it has an absolute minimum of 0 and an absolute maximum of 1. Now, here are some examples of functions with absolute maximums, minimums, or no absolute maximum and minimum. If you look at the A graph, it has an absolute minimum only. We are looking at the graph of y equals x squared with the domain between negative infinity and positive infinity. And it has a low point there at y equals 0 and x equals 0. Now look at the graph in B. Here we're only looking at the domain of between 0 and 2. So the piece here that's a little darker, we're only looking at that piece. It has an absolute maximum here and an absolute minimum here. So it has an absolute maximum of 4, 2 squared, an absolute minimum of 0, 0 squared. Now if we look here from 0 to 2, and notice there's a parenthesis on the 0 and a hole there at 0. That means there's no absolute minimum on this graph. There's no lowest point on this graph as there is here where this is shaded in. There is an absolute minimum here at 4, or I'm sorry, an absolute maximum here at 4. If you look at graph D, it does not have an absolute minimum or an absolute maximum because it's the domain from 0 to 2 with 0 and 2 not included. Now, the extreme value theorem says if f is continuous on a closed interval. Now that's important because notice some of the examples from the previous slide were not closed intervals. But if we have a continuous function on a closed interval, then f attains both an absolute maximum value and an absolute minimum value in that range. There are numbers, x1 and x2, between a and b, where f of x1 is the minimum and f of x2 is the maximum. And m is less than or equal to every y value except m, and capital M is greater than or equal to every other y value. Now here are some more examples of graphs with maximums and minimums. And we're looking first at the A graph that goes from A to B here. It has an absolute maximum here at x sub 2, and the actual maximum is capital N. Then we have an absolute minimum here at x sub 1, and the absolute minimum is m. Now, this graph has maximum and minimum values on the interior of our domain. Now look at this example. Here our maximum is at one endpoint and our minimum is at another endpoint. So you can have the maximum and minimum both as interior points or both as endpoints. You could also have an example like this where the maximum is an interior point and the minimum is one of the endpoints. So this is the highest point on the graph and this is the lowest point on the graph. Or like here where your minimum is on the interior and your maximum is at an endpoint. So these are some possibilities for continuous functions, maximum and minimums on closed intervals. Now look at this example. This is a piecewise function. Notice that it has a smallest value, and the smallest y value is 0. And it occurs at x equals 0 and at x equals 1. However, it does not have a highest point. What would have been the highest point has a hole here. So there is no highest point on this graph. This is a discontinuous function, and this example shows us that anytime there's a discontinuity that previous theorem does not hold. It has to be a continuous function. Now we talked about absolute maximums and minimums, which were the absolutely largest y value on the graph and the absolutely smallest y value on the graph. We also want to look at local maximums and minimums. Now function f has a local maximum at an interior point C of its domain if all the y values around it are less than or equal to its y value in some open interval. And it has a local minimum value at an interior point C of its domain if its y value, if all the y values are greater than that y value on some open interval. Now the easy way to think about this is looking at a graph as having hills and valleys. A maximum is just any little hill in a graph. So where our graph starts increasing, gets to a high point, and then starts decreasing, that would be a maximum. Here's another maximum. It starts increasing and then decreasing. Now for local minimum, a local minimum is any value where you are decreasing and then you start increasing again. And you'll notice if you take just a little interval around each one of these, this would be the highest point in that interval for here and here, and this would be the lowest point in a little interval around it. Now look at A. A is the absolute minimum. It is the lowest point on this graph. And D is the absolute maximum. It is the highest point on this graph. But we also have local maximums, local minimums. This is also a local minimum because it's a low point. So you can have a local minimum as an endpoint. Now the first derivative theorem for local extreme values says if f has a local maximum or minimum value at an interior point C of its domain, and if f prime is defined at C, then f prime of C equals 0. What that tells us is that if we have a local maximum or minimum at an interior point and f prime is defined, then the slope of the graph there is 0. If we go back one slide and we look at these three places in the interior where we have local maximums and minimums here, you can see that the slope of the graph is 0. Now here, remember, when you have a point, the slope is not defined there. There is no derivative when you have a point like this. But if you look at these two, the slope of our tangent lines are 0 at the local maximum and at the local minimum. Here's another example. You can see that you have a slope of 0 at this local maximum value. Now, if you have a derivative of 0, that does not necessarily mean that there has to be a maximum or minimum there. If we take the graph at the top, which is y equals x cubed, and we take its first derivative, that will be 3x squared. And we think about where is that first derivative equal to 0? Well, if I divide by 3, I'll have x squared equals 0. Take the square root, and x will be 0. But we can see here at this point on the graph that it does not have a maximum or minimum value. Okay? What the theorem told us that if there is a maximum or minimum value, then the slope there is 0. But it did not say that everywhere that the slope was 0, that it had a maximum or minimum. So it's real important that you notice the distinction there.